So now we move with Marika Giuletti. If you can share the screen.
Yes.
She will talk us about ALMA resolves the first optical near-infrared dark lensing system.
Okay,
So the
thank
floor is
you.
yours.
Can you hear me well? Can you
Yes.
see the screen? Okay,
yes.
Perfect. Okay, so hello everyone. Thank you so much to the organizers for having me here. I'm Marika Giuletti and I'm a PhD student at SISSA in Trieste. And today I will talk about the first optical near-infrared dark lensing system resolved by ALMA. And okay, first of all, I would like to start with a bit of an introduction, just on the framework in which we are moving. Especially, we'll be talking about dust sister-forming galaxies, which are a population of galaxies known to be a strong contribution, to provide a strong contribution to the star formation history at redshift between 2 and 4. They are also detected up to higher redshift, up to redshift 6. And they are also thought to be the progenitors of the quiescent early type galaxies. And for these reasons, this population of galaxies is particularly important to test, for example, co-evolutionary models between supermassive black holes and their host galaxies. Indeed, some degree of co-evolution seems to be present. For example, in the top plot, you can see the behavior of the star formation rate density as a function of the redshift, and in red, and the blue line, the black hole accretion rate density, which feature similar trends. Moreover, as part of this more general population of dust star-forming galaxies, in the last years has become more clear that objects which are selected to be dark in the optical and the near-infrared regime, so in the rest frame UV, are found to provide a significant contribution to the star formation rate density, given to very high redshift, for example, redshift 6, with respect to the population, the well-known population of rest frame UV selected galaxies. So they are known to be extremely important in the context of galaxy formation and evolution. But if we want to study these objects in the details, in particular on the physical properties and their interstellar medium, their morphology, we need especially to solve the observations. The main problem with that is that the high redshift dust star-forming galaxies are extremely compact, with typical sizes of a few kiloparsecs, which corresponds to a few tenths of an arc second at redshift 2. Therefore, very hard to resolve even for the most modern instrumentation and facilities. Fortunately, we have a great help coming from a physical phenomenon, which is the gravitational lensing. Indeed, the mass of a foreground object can distort the fabric of the space-time, and as an effect, the light coming from a distant object results in an increase in its luminosity by a factor which goes as linearly as mu, which is the magnification factor. And moreover, multiple images are created, and the sizes of the background source appears stretched by a factor which goes as mu to the 1/2. In particular, for this talk, I will focus on the galaxy strong lensing cases. And to go more deeper, this talk will focus on a peculiar object, which I will call J1135. This object was originally selected in the Herschel Atlas survey, which was already introduced this morning by Corino D'Amato, and also the survey source is placed in this context. And if you want to know more about shores, please invite you to follow also Mariam Behiri's talk on Thursday. And this object was inside a sample of candidate strongly lensed galaxies selected in the Herschel Atlas survey by mainly two works by Negrello et al. 2017 and Ward et al. 2022. And for more details on this selection, you can follow Martina Torcello's talk tomorrow. And this object The nature of this object has been longly debated for several years, mainly because of the lack of clearly resolved observations, for example, in the submillimeter by submillimeter array. And what was new was that the redshift of the background source was spectroscopically confirmed by CO observations, while the redshift of the lens was completely unknown. And as a peculiarity, this source is one of the most bright in the far infrared among the whole sample of candidate strongly lensed galaxies. What we found in the ALMA archive was the presence of high quality, high angular resolution and sensitivity data in 3 different bands, in band 8, 7, and 6. And as you can see, the angular resolution is quite high, reaching up to 0.09 arc seconds. And with these ALMA observations, we were immediately able to confirm the lens nature of the systems. And of course, since the nature was strongly debated in the years, no previous lens modeling was performed before, and we will also see why. Together with continuing observations, ALMA archive provides us with extremely bright C+ and CO87 lines were resolved, and extremely bright because of the magnification of the lensing. And together with the spectral lines, we also have ancillary observations, multi-band observations from hypersupreme cloud surveys, from Hubble Space Telescope, Viking surveys in the near infrared, also IRAC channel 1 and 2, and also other archival observation at 6 centimeters for the radio band from AVLA. And in particular, for the Hubble Space Telescope image, we will see why this object is extremely peculiar. Indeed, what one would expect by looking similar observations in the Hubble Space Telescope for similar objects, for example, here I reported 5 strongly lensed sources among the Herschel Atlas survey, is the presence of the foreground object, which is often a massive elliptical redshift between 0.3 and 0.8. And in the background, always in the near infrared bands, is visible you can see the Einstein ring from the background source, originated from the background source. What we see indeed for J1135 in similar Hubble Space Telescope observations is basically almost nothing. So there is no clear counterpart in the J band, nor for the source, but even more interestingly, also anything is visible from the foreground lens, which is something really strange. Okay, so the ALMA data were so good that we were able to perform the lens modeling. So to this purpose, we use PyAutoLens, which is an open source code written in Python for a strong gravitational lensing. We reconstructed the background source morphology from the lens modeling for the band 8, 7, and 6 continuum. Here I reported the band 8 continuum and the C+ and the CO87 lines. As you can see, we were able to infer a really compact morphology for the dust, which reaches up to 500 parsecs, and a slightly more extended emission from the gas component. Moreover, we performed cinematic analysis for the CO87 data by dividing the spectral line in 3 different velocity beams and reconstructed the lensed morphology. What we retrieved basically is that there is no clear evidence for a stronger rotation or outpose. Then, by exploiting the multi-band counterparts available for this source, we performed the CD fitting. We figured indeed that this source is really dusty. It has a really high dust and gas content. Gas masses were inferred by several tracers. And it is also a really star-forming object with a star formation rate which goes up to almost 100 solar masses per year. For what concerns the stellar mass, we infer basically an upper limit because of the lack of a clear counterpart in the near-infrared optical regime. and therefore the estimating output from the SD fitting must be considered as an upper limit. Okay, so as a next step, we try to interpret, to give an evolutionary interpretation of this object. We Rino this morning told you about the in situ model, and what we did was basically to put together all the physical properties we retrieved. For example, for the source reconstruction, we were able to compute the star formation surface density, which is a value which is well above the Eddington limit for a radiation-supported starburst. Also, the depletion timescale and the star formation timescales points towards an off-main sequence young and compact starburst, which is well above the main sequence for similar objects redshift 3. Therefore, by interpreting this, we found that this source can be compatible and interpreted as a source facing a compaction stage as predicted by the in situ model, so it's increasing its stellar mass content and still has a huge gas reservoir, so it must double its stellar mass before the quenching from the central nucleus of Earth. Okay, so now you're probably wondering, what about the lens? Well, as I've mentioned before, no clear detection for the lens source is available. We do not have any redshift estimates, and this is extremely rare. And also, in some cases, this is really difficult to characterize. And what one should do in such cases is what is called lens subtraction. So, subtracting the contribution from the foreground object to the background source in order to perform an accurate SD fitting. In this case, it was not necessary, since we constrained from the lens modeling, so the Einstein total gravitational mass, and we were able to recreate, to assume a spectral energy distribution template for the foreground object, by assuming it is an elliptical galaxy, as almost in all other similar cases. And what we infer is that if this source is indeed an elliptical galaxy with that mass, it should be at around redshift at least 1.5, even more. So at the end, yeah, thank you. At the end, no significant contribution from the foreground object was found, so no lens subtraction was needed. And to characterize the nature of this source for the foreground lens, really JWST will be crucial, in particular NIRCam and NIRI observations, in particular NIRCam for the lens object to assess the nature, to see whether our assumptions are correct. And NIRI could be crucial for the characterization of the possible mid-infrared excess originated by the possible presence of an AGN for the background source. Then a bit prospect of what we are doing right now for this source, together with the CO and C+ observations in the same ALMA data, we also have waterline emission, free transitions in particular, and you can find the results in the next future from this work led by Francesca Perrotta. And the main goal of this work will be basically reperform a similar analysis as we did for the continuum and the CO and C+ data, and reconstruct the morphology of the different waterline transitions. Since we have this galaxy, this galaxy is featuring a huge dust content, it's really important to characterize the processes which lead to the excitation of these lines, which can be very different, not only the so-called far infrared pumping, but also different processes such as collisions. And let me also stress that this is an analysis which today it is limited for only nearby sources in the local universe, mainly because of problem of angular resolution. And with ALMA and the combination of ALMA data and the strong gravitational lensing, it is now possible to characterize water lines also in distant galaxies with such level of details. Okay, so I will leave you here with my conclusions. If you are curious to know more about my work, you can find me here. And also let me just stress that thanks to ALMA and the ALMA Science Archive, we were able to characterize this and study this peculiar lensing system. And we hope in the future that JWST will be crucial to know and shed more and shed new light on this object. Thank you.
Thank you, Marika.
Thank you.
There is a question in the chat by Abject Worker. I don't know if you want to say or I just read it. Okay, I read it. So I was surprised to see such strong lensing being caused by apparently a single massive galaxy. Are there other cases like this that you know of?
Yeah, indeed, the magnification factors that we retrieve is consistent with other similar cases. For example, in the Herschel-Atlas surveys, there are for the Herschel-Atlas surveys there are other similar cases such as STP81, which is maybe you're more familiar with, also STP9, etc. And in some of these cases, the magnification factors are even higher, and the lensing source is basically a single elliptical galaxy.
Okay, thank you. There is Melanie.
Hey, that was really beautiful data. I have a question about the CO8-7 versus the C2. It looked to me like the C2 was more compact in the image that you showed. Was this just a... Yeah, exactly. Was this just a resolution effect, or what's the... I mean, I'm struggling to explain that.
Yeah, we are working on that, but our main thought is that since the resolution is really different, not so different, but it is different between the different data, in particular CO and C+. It may reflect also on the lens modeling and the source reconstruction, which is basically a geometrical reconstruction of the morphology. So it is possible that it is a consequence of the different angular resolution of the observations.
If I can follow up on that, actually. So with Pi Auto Lens, you modeled the lensing in the image plane, right? Did you also do this for the UV plane?
Yeah, no, it was done, sorry, all in the UV plane.
Okay, thanks.
Directly, yeah, you're welcome.
Great.
Another question by Gayardi Guruyan. Hi, Marika, great
Hi.
talk.
Thank you.
Sorry if I missed it. Did you find any effects of differential magnification between the CO, C2, and continuum?
Well, I've reported here the different magnifications we have retrieved for the 3 different data. We didn't perform an in-depth analysis of differential magnifications, but yeah, it is something worth doing in details, maybe in the future. I mean, just to assess whether how the magnification is distributed. I mean, the lensing plane.
Perfect. Thank you very much.